Very good. That is really dog and bugs. Genius.
Welcome back to McGrathmatics for our next lesson in mechanics. We're starting off with a couple of integration flashback questions because if you're not real good at integral calculus, mechanics is very challenging. So, a couple of more questions, a 3-marker and a 4-marker. Let's start off with the 3-marker. As always, if you feel like you have an idea of how to approach this, pause the video, have a go, and then compare our solutions and see how you went. So, for the first one, whenever I see a fraction with like a 1 plus cos or a 1 plus sine or maybe a 1 plus cos plus sine, in that form, especially with limits between 0 and pi on 2, this is screaming out that it's a question involving t-values. Sometimes the questions will be nice and they'll tell you to use t-values, but sometimes the more challenging ones will require you to recognize it yourself and apply the substitutions from your reference sheet. So our substitution is we're going to let t equal to tan of x on 2. If you look at your reference sheet, you'll find that cos x is equal to 1 minus t squared over 1 plus t squared. But the one you have to memorize is that the dx is going to be substituted to 2 dt over 1 plus t squared. Easy way to memorize this is that it's just the substitution for sine with a d on top as well. So sine is 2t over 1 plus t squared. That's how I remember it anyway. We'll also fix up our limits because we are making a substitution. So we'll turn these two x values into t values. So we'll do tan of pi on 2, which is tan pi on 4, which is tan 45 equal to 1. And for the second one, we're doing tan of half 0, which is tan 0, which is equal to 0. So our limits are going to become 0 to 1. And we're going to substitute these two values into our integral, which looks like this. So a bit of a mess currently, but what we can do to simplify is we can multiply the top and bottom of the fraction by 1 plus t squared to get rid of these denominators and turn this 1 into a 1 plus t squared. So multiply everything by 1 plus t squared, and it looks like this. Top becomes 2, this part becomes 1 minus t squared, and this 1 becomes 1 plus t squared. Super convenient because the t squared and the minus t squared cancel out, so we get 2 over 2, which is equal to 1, and so now it's a very easy integral. We just integrate 1 into x, and we do 1 minus 0, and we end up with a final answer of 1. So if you got 1, congrats on your 3 marks. I plagiarized these from some random trial paper that I can't remember, but they are not HSC questions, they're HSC style. For the next one, 4 marks, integrating between 0 and pi on 4, we've got tan cubed x times sec to the power of 4x. So straight away when I see an integral like this, I keep in the back of my mind that, hang on, sec squared is the derivative of tan cubed. So if I can somehow turn this into an integral involving a function of tan multiplied by sec squared, I can apply a substitution that's going to make things a lot simpler. So what we'll do is we'll split apart this sec to the 4 as a sec squared times sec squared, because we also know that another way of writing sec squared is 1 plus tan squared using our Pythagorean identities. So I'm going to write that sec squared in the middle as 1 plus tan squared. So now I have a function of tan multiplied by sec squared dx. So it's telling me that now the smart move is to make the substitution u equal to tan x. So we're going to have u cubed here, we're going to have u squared here, and if we differentiate our substitution, we get the derivative of u is equal to sec squared dx, which is what we have right on the end, so it works out really nicely. So summing that all in, our limits are going to turn into tan of 0, which is 0, and tan of pi on 4, which is 1 once again. Now we just have an integral involving u's. We could just expand this out and use plain old regular integration to get our answer. So we have u cubed plus u to the power of 5. Integrating these, they become u to the 4 on 4 and u to the 6 on 6. If we sub in our 1, when we sub in 0, we're just going to get 0, so we can just ignore it. We're just going to sub in 1 and get our final answer for 4 marks equal to 5 on 12. Okay, enough warm up. Let's dive into our next lesson. Today we're looking at projectile motion. So hopefully you've already encountered a bit of this in the Extension 1 course. Today's just going to be looking at some harder examples, looking at some HSC questions of Extension 2 level projectile motion questions. Later on in a couple of weeks, I'll hopefully have time to do a video on resisted projectile motion, which will be the last lesson in the course. Okay, so I'm assuming for this video you already have a bit of background knowledge on projectile motion, but if you don't, maybe go back and look at an Extension 1 video or do some study. Anyway, first example from the 2020 HSC Extension 2 exam. I would say this is categorized as a fairly straightforward projectile motion question, which hopefully you'll see, but let's dive into it. We've got a particle starting from the origin with velocity u, acceleration vector given by no horizontal acceleration and minus gravity vertical acceleration. So from this and the initial conditions of 0, show that the position vector is given by this. So quite often in questions, they will give you the equations for x and y. In this question for 3 marks, they're asking us to derive them by going from acceleration through to velocity up to displacement. So let's do that. An important part of this is setting up your initial conditions for velocity. So our initial velocity of the particle is u. We're going to split this into a triangle where the angle of projection is equal to theta. So we're going to get 2 expressions for our horizontal and vertical initial velocity. We're going to have across here, we're going to have u cos theta because this is the adjacent side to the angle theta. So it's hypotenuse cosine of the angle. The opposite side to theta is going to be hypotenuse times sine of the angle. So there is our initial vertical velocity, and here is our initial horizontal velocity. So let's start by deriving our expression for the horizontal displacement. So we'll start with our horizontal acceleration, which the question said was 0. So we're going to go from acceleration to velocity by integrating. When you integrate nothing, you get nothing, and then you add a constant. Now, because we're showing here that our velocity is constant, it means our velocity is not changing, which means it must always be equal to the starting value, which is u cos theta. Okay, so that's a bit of basic knowledge of projectile motion, that there is no change in velocity in the x direction. It always moves left and right at the same speed if there's no resistance, which for this question, there is none. So here is our velocity. We are going to integrate this once again to get to our displacement. So displacement is the integral of velocity with respect to time. Now, because this is a u and a theta, this has got nothing to do with t. This is just a constant. So when we integrate a constant with respect to t, we just give it a t and a plus c. We'll figure out the constant with the initial conditions, that initially the particle was at the origin. So when t equals 0, x equals 0. This gives us that c is equal to 0, which gives us our x displacement ut cos theta as required in the question. Now we'll finish off by doing the same thing with the vertical component. So our vertical velocity initially, well, the whole time, is equal to gravity in the negative direction. We will integrate this to establish our vertical velocity. So that's y dot. So integrating minus g with respect to t, we give it a t and we plus c. Why am I rhyming? Anyway, let's keep going. All right, let's figure out our constant by subbing in the initial conditions. So initially, when t is equal to 0, our y velocity, as we established in this triangle over here, is equal to u sine theta. So when t is 0, vertical velocity is u sine theta. This gives us that the constant value on the end is equal to u sine theta, which gives us this as our vertical velocity. So now we'll integrate this with respect to t to get our vertical displacement. So we're going to get minus g t squared on 2. And then the u sine theta, once again, is a constant, so it's going to get a t. And then we'll put a constant on the end, which will show as 0 by subbing in our initial conditions. Once again, initially, we're at the start of the particle, we're at the bottom, so it's y equals 0. This gives us that the constant must be equal to 0, which means this is our y displacement as required by the vector in the question. So there we have shown the 2 components of our displacement position vector for 3 marks. Part 2, pretty common question in HSC exams is show the Cartesian equation is given by this. So Cartesian equation involves no t's, it's all x's and y's. So what we're going to do is we're going to take our y, we're going to take our x, which we derived in the first part of the question, and we're going to combine these together. Usually the easiest way to do that is to take your x equation, which is more simple. We are going to rearrange this to make t the subject, and we're going to substitute that into our vertical displacement. So rearranging this, we get x divided by u cos theta is equal to t. Substituting this into our expression for y looks like this. So we're putting it here and we're squaring it here. Now we're just going to try and make this look like this if possible to get 3 marks. So we've got u divided by u cancels out. Sine over cos we can write as tan. And on the end here we've got x squared over u squared cos squared. So we're looking at that now. So we have a tan here, we have a cos squared. We want to have an expression only involving tan. So what we're going to do now is we are going to factor out the thing that they want factored out the front of the whole expression. So the thing we're aiming for has a negative gx squared over 2u squared out the front. So we're going to factor that out of both terms. It comes pretty naturally out of the cos squared because it's got everything. It's got gx squared, 2u squared with a negative, so that goes out the front. To pull it out of the x tan theta, it's missing some bits, so we sort of fill in the gaps with the reciprocal. So imagine if we expanded these terms out, the x squared would cancel with the x, u squared cancel out, g's cancel out, we'd end up with this. So we're kind of factorizing by creating our own sort of stuff in there that we can pull out, if that sort of makes sense. Okay? So here is this expression down here with a negative gx squared over 2u squared factored out the front, reverse expanded. Now we're trying to get everything involving tan squared, so we're going to write 1 over cos squared as sec squared, because we are very clever and we know our trigonometry, and we know that sec squared can also be written as 1 plus tan squared. Okay, don't forget, a man and a tan is sexy. So writing the sec squared as a 1 plus tan squared, it now looks like the target in the question. So we have got our 3 marks in the 2020 exam. So we just got 6% in like 4 minutes. So good. Moving on to part 3. Given that the initial velocity squared is greater than gravity times r, prove that there are 2 distinct values of theta for which the particle will land at x equal to r. Okay, so if we are landing at r, that means our horizontal displacement will be equal to r, and our vertical displacement, because we're landing, will be equal to 0, because we're landing back to the starting point on the ground. So we can say when x is equal to capital R, y is equal to 0. These are the 2 values we are going to substitute into our Cartesian equation from before, and we're going to show that this equation has 2 distinct solutions for theta. Okay, so here is the Cartesian equation for part 2. I've changed the x's to capital R's, and I've set the y equal to 0. So the goal now for 2 marks is prove that this quadratic equation has 2 solutions, given that u squared is greater than gr. So solving this, we can divide by the constant out the front, just to make it look a little bit nicer. And now looking at this quadratic, if we're trying to show that this has 2 solutions, the quickest way to do that is to show that the discriminant, which is the part inside the square root of your quadratic formula, show that the discriminant is bigger than 0, and that's going to tell you you've got 2 solutions. Okay, so here's our discriminant. We've got b squared minus 4ac. The b is in front of the tan theta, the a is in front of the tan squared, which is 1, and the c is on the end. Okay, so this is the part inside the square root of the quadratic formula. Negative squared is positive. We get 2 times u squared squared, which is u to the 4, over g squared r squared. Take away 4. So now we are trying to show that this is greater than 0, so that our discriminant is positive, so that this quadratic equation has 2 solutions. So using the conditions in the question, u squared is bigger than gr. This means if we square both sides, u to the 4 is bigger than g squared r squared. I'm trying to make it look like this, remember? Okay, so that means that if we divide both sides by g squared r squared, we get greater than 1. And now we'll multiply both sides by 4. And now we'll bring the 4 across. And what do you know? 4u to the 4 over g squared r squared minus 4 is bigger than 0, which means our discriminant is positive, which means that our quadratic has 2 distinct solutions for theta. So we have done the question for 2 marks. Beautiful. Okay, moving on to example 2. So this is an example from a old extension 1 paper. It was the last question in the exam, so it's pretty spicy, especially the final part, which is a band 6 question. So let's just rip in. We've got a paintball fired from the origin, 14 meters per second, angle of theta, hits a barrier, and the barrier is 10 meters from where we started. They've given us the equations of motion. We don't need to prove these. They've already derived them for us, which they usually do. Okay, now we're going to use these equations. So the height of the wall is 8 meters, in case you were wondering. Part I, show that the equation of the trajectory of the paintball is equal to this. So what we're seeing here is an equation relating y and x. So this is similar to part 2 from the last example. This question is basically trying to get the Cartesian equation. We're trying to combine the y and the x together to get one equation. So here's our y, here's our x. Just like last time, we are going to rearrange x and substitute this into y. So rearranging the second equation, we get t equal to x divided by 14 cos theta. Substitute this into the vertical displacement up here. So we're changing the t's to x over 14 cos thetas. All right, 14's cancel out. Sine over cos, once again, is tan, and we're going to get x squared times 4.9 over 14 squared cos squared. 4.9 over 196, I believe, is 1 over 40, probably, because there's a 40 here. Yeah, it is. Okay, so the sine over cos turns into a tan, so we have x tan theta. We have minus x squared over 40 times, once again, writing cos squared, 1 over cos squared as sec squared. Using the trick from before, we can change the sec squared to be a 1 plus tan squared using our identity. And the question said we can let tan theta equal to m, so we'll change that to an m, change that to an m, and then we get the target required in the question. Okay, 2 marks, nice and easy. Moving on to part 2. Show the paintball will hit the barrier at height h, so like just here, this is h, when m is equal to 2 plus or minus square root of 3 minus 0.4h. Hence, determine the maximum value of h. This is a bit of a stitch up for 2 marks because there's a fair bit of work to be done here, but let's quit one and start getting into it. So we have our equation relating y and x. Now, we are hitting the barrier at a height of h. That means when the x displacement is equal to 10, the value of y is going to be equal to h. Okay, x equals 10, y equals h. Let's substitute that into this equation right here. And now we are trying to solve for m and get this value right here. Okay, so we're going to tidy up this quadratic as best we can. So what I'm going to do is multiply everything by 40. So we get 40h, 400m, and then negative 100 times 1 plus m squared. Going to expand this out and just divide everything by 10 apparently. Yeah, divide everything by 10 because we've got a common factor of 10. So we get 4, 40, 10, 10. Rearranging this, everything on one side and dividing everything by 2 because we've got 4 even numbers. We get 5m squared on the left. We get negative 20m on the left. We add the 5 across and this 4h turns into a 2h. And now we have a quadratic equation. We've got an a, a b, and a c that we can solve using the quadratic formula. So quadratic formula, we've got negative b at the front, inside plus minus square root of negative 20 squared, minus 4 times 5 times c. Now the c is everything left over without an m, so it's the 2h plus 5. That's your constant on the end. All over 2 times 5. So solving this, we get 400 minus 40h minus 100 inside our discriminant. So this will turn into a 300 minus 40h. We can see inside the square root, we want to have a 3 minus 0.4h. So what we'll do is we'll factor 100 out of the square root. And when you pull the 100 out of the square root, it turns into a 10 because the square root of 100 is 10. Fun fact. So factoring the 100 out turns into a 10. Now we have a common factor of 10 everywhere. So we can divide everything on this fraction by 10. So we get 2 plus or minus 1 times root 3 minus 0.4h all over 1, which was the target in the question. Now, for all that work, that only got us 1 mark because it's a 2-mark question and there's 2 things to do. It says, hence determine the maximum value of h. So we're trying to find the biggest number that we can put into this square root that's going to give us an actual answer because we want to actually have a value of m so that we, pass through the hole. We hit h, basically. Okay, so move that over there. Determine the maximum value of h. We need what's inside the square root to be positive or 0 because we can't do the square root of a negative number because then we get no solutions and this whole thing doesn't work. So solving this, we're going to put the negative 0.4h across. We're going to turn everything around and then divide both sides by 0.4. And you get h must be less than or equal to 7.5, which tells us that the biggest possible value that we can put into this that gets us an answer is h equal to 7.5. And that's your second mark. Okay, on to part 3. There's a large hole in the barrier. The bottom of the hole is 3.9 meters above the ground and the top hole is 5.9. The paintball passes through the hole if m is in one of these 2 intervals. One of them is 2.8 and up to 3.2. Find the other one. So here is what we are looking at. There's one value that hits the bottom, but then anytime you want to hit some point on a projectile, there's 2 angles that can get you there. It could be this angle here, or it could be this dotted line at the top. Hits us there. Okay, for the top, 5.9, we could pitch it at this angle, which is going to be an m value. So keep in mind for all this question, m is just equal to tan theta. So m is really just a kind of expression for the angle of the projectile, essentially. Okay, one value of m gets us there, and another value could be pitched up and also hits the top right there. So the 2 ranges we're looking for are between these 2 black lines and between these 2 dotted lines. The question's already given us one of them. We just need to find the other. Okay, so we'll go to our value from before. This is our expression for m. So this is m when we sub in a value for h. And we know what h needs to be. It needs to be either 3.9 or 5.9 to get us within this this range here. So we'll start off by subbing in h equal to 3.9. This will give us 2 solutions because we've got a plus minus. So we're going to get m equal to 2 plus or minus 3 minus 0.4 times 3.9. This works out to be 2 plus or minus 1.2, which gets us 0.8 and 3.2. So they already got the 3.2. We've got the other one, which is 0.8. Okay, so 0.8 is just here and 3.2 is up here. Okay, this m value gets us there. The other m value gets us the dotted line and hits us there. Let's find the other one. The top of the range is 5.9, so we'll sub 5.9 into our expression for m. Doing the calcs, we get an expression for 2 plus or minus 0.8, so we get 1.2 and 2.8. So that's these 2 lines just here, okay? This one here is 1.2 value of m, gets us there, and then 2.8 value of m gets us there. Lovely, so they already told us that one range between the 2 dotted lines is 2.8 to 3.2. So from our numbers, we can conclude that the lower range, the 2 thick black lines, must be between 0.8 and 1.2. And that is our interval to get 2 marks for this question. On to part 4, which is the pretty spicy band 6 part. Let's see if I can work through it. We've got show that if the paintball passes through the hole, the range is equal to this. Once we've done that, find the two widths of the interval in which the paintball can land at ground level on the other side. Okay, so we're passing through the hole and then we're landing on the other side, and we're trying to find the range or the width of the interval that we could land in based on our values from M that we established in the last question. Okay, so when you're trying to find the range of a projectile, what you're trying to find is where the y value is equal to 0, because range is where you land, and that's where your vertical displacement goes back to being 0. So we'll take our Cartesian equation from the earlier part of the question. We'll set the y value equal to 0, and we're going to try and solve for x and show that we get this value here. Luckily, we've got two factors of x because it's a fairly nice quadratic, so we can just go through and divide everything in this equation by x, and we get m minus 1 plus m squared over 40 times x. We're going to chuck this across to get 1 plus m squared x over 40. Solving for x, we just need to multiply by 40 and then divide by 1 plus m squared, and then we get the target from the question for the first mark. Okay, now for the last 2 marks in this question, we need to find the ranges. So here is our expression. If we sub in an m, it gets us the x value where we land. So we're going to look at the 2 endpoints of our intervals that we established in part 3 to see how far away we're landing, to see how wide our interval is. So for our first interval, 2.8 and 3.2, we're going to substitute these 2 m values into our expression for the range and see what we're working with. When we sub in 2.8 into this, we get about 12.7 or 12.67. When we sub in when we sub in m equal to 3.2, we get a value of x around 11.387. Okay, that means the range, or the range of the interval in which we could land between these two values, is 12.669, take away 11.387, which gets us an answer around 1.3. All right, so we've got a landing range of 1.3 meters. Now that's not too spicy. The tricky part, the band 6 part, is the next interval where we're going between 0.8 and 1.2. When we sub in 0.8, we get about 19.512. When we sub in 1.2, we get about 19.672. However, the trick is, how do we know that this is the earlier value and this is the later value? How do we know if there's a value between 0.8 and 1.2 where the projectile will be further away? That's what we need to think about here, because m is actually equal to tan theta, which means that the maximum value of m is going to be equal to 1. The reason for that is because if you want to get the maximum range out of your projectile, it's going to be pitched at 45 degrees. Okay, exactly halfway between 0 and 90 is where you're going to get the biggest range from your projectile. So the largest range occurs at theta equals 45. That means the largest range for m, because m is equal to tan theta and tan 45 is equal to 1, that means m equal to 1 is going to get us further away from the start point as possible. That's important because m equal to 1 is within the range of 0.8 and 1.2. So 0.8 and 1.2 are not the endpoints. We're going, starting at 0.8, we go up to 1, and then we go back to 1.2. So if we want to find the maximum range in which we can land in this interval, we've got to look at the largest value for m, or largest value for range, I should say, which is m equal to 1. Okay? So when we sub m equal to 1 into our range formula, we get 40 over 2, so we actually get up to 20. Okay, so the smallest value is 19.5 and the largest value is 20. So to get full marks for this question, you've got to recognize this step here and get the actual maximum range of 0.5. So it's not the distance between these two, it's the distance from 19.5 up to 20. Okay, so that's what makes this a bit of an extra spice question, because you've got to keep in the back of your mind, oh, hang on, what if there's a larger value between 0.8 and 1.2, which in this case, there is. Okay, hopefully that made some sense. Moving on to the last example, Lord help me, it's the 5 marker from the 2021 Extension 2 HSC. So what we're going to be seeing in HSC papers from now on is that there will be one 5-mark question in every exam, standard, advanced, and Extension 2. This was the Extension 2 one from last year at the time of recording this video. We've got a particle, bloody blah, all the usual stuff, gravity picture right here. They have given us the position vector, so we're not required to derive our horizontal and vertical displacement, given to us nice and easy. Now here's the important part. For some values of theta, there will be 2 times during the flight when the particle's position vector is perpendicular to its velocity vector. Find the values of theta when this occurs and justify that both times occur during the time of flight. Okay, so we're going to start off by finding the values of theta that make our displacement perpendicular to our velocity. That's where we're going to start for this 5-mark behemoth. Okay, so here is, oops, spoiler, here is our displacement vector given to us by the question. we are going to differentiate both of these so we can get our velocity. So we'll differentiate these with respect to time, and we get our velocity vector. So we get u cos theta, and we get minus g u sine theta. So the question said there are some values of theta where these two vectors are going to be perpendicular. Hopefully you've done a bit of extension 1 study, and you know that perpendicular vectors, when you do their dot product, you get a value equal to 0. So we're trying to find when is the position dot product with the velocity equal to 0, which looks like this. So dot product is multiply your x values, multiply your y values, and then add them together equal to 0 because we are perpendicular. All right, so evaluating our dot product, at the front we get u squared t cos squared. And then if we expand out all this mess very carefully, we end up with positive gt cubed over 2. We get negative gt squared on 2 times u sine theta just here. We get minus gu t squared sine theta in the middle. And then on the end, we're going to get u squared t sine squared. So the goal is to tidy this up as best as possible and try and solve this equation to establish some values for theta, which is a bit of a task, which is why this is band 5, 6 level question, but we love pain. That's why we study extension 2 mathematics. Something cool we can do is we can group together the u squared t's out of the sine squared and the cos squared because we've got a common factor. That's convenient because because cos squared plus sine squared is equal to 1. So this part's just going to turn into an invisible 1, leaving us looking like this. Oh, spoiler. Okay, so now for the next part, here is our tidied up quadratic as best we can. So I've turned this into a 1. I've multiplied everything by 2 to get rid of the fractions. And what else have I done? There's also a common factor of t. So I've divided everything by t to bring down the power a bit. So I've reduced the power by t for everything. And I think that's all I've done. Yeah, 2u squared t. Cool, so turning this into a 1, multiplying everything by 2, and dividing everything by t gets us from this line to this line. Now we have a quadratic in terms of t. We've got t squared and t here, which is what we're trying to solve for. Okay, so now the question said there are 2 solutions, okay, which means that our discriminant needs to be greater than 0, so we get an actual answer in our quadratic formula. So evaluating the discriminant of this mess right here. Pardon me. All right, so our b, which is in front of our t, which is the minus 3 ug sine theta, that's our b right here. So we've got b squared minus 4 times a, which is the g squared, times c, which is the 2u squared. Okay, now this expression is going to be greater than 0 because the question said there are 2 times at which these 2 vectors are perpendicular, which means they're equal to 0, the dot product. So it's all coming together now. Simplifying this, we get 9u squared g squared sine squared, and we get 8g squared u squared greater than 0 here. All right, factoring out the u squared g squared as a common factor, and now we have u squared g squared, which is positive because u is positive and g is positive. We've got this multiplied by this is greater than 0. So if we've got a positive multiplying by something, and the answer is greater than 0, what's inside this bracket needs to be positive, otherwise that doesn't work. So we can say 9 sine squared theta minus 8 is greater than 0, which means we can say that sine squared is greater than 8 over 9. Okay, so saying this bracket is greater than 0 allows us to say this, which gets us that sine is equal to square root of 8 over square root of 9, which is just here. We'll take sine inverse of both sides, and then we get our expression for theta. Okay, we know this is only going to give us one answer because we know from the question that the angle theta is acute. It's between 0 and 90. So theta is acute, so this answer is only one value. Okay, we're making progress now. What are we doing next? I forget. Let's have a look. All right, so now we just need to check that this time of... So the second part of the question is show that there's 2 values of theta for which they are perpendicular. We've done that. Now we just need to check that the times actually occur within the flight time of the projectile. Okay, so the way we're going to do that is we're going to find the time at which this projectile lands and show that our time from before, which we can get by solving this equation, we're going to show that that time is less than the time taken for the projectile to land, so that these both occur within the flight time. Okay, so the way we find the flight time is we look at where the y velocity is equal to 0, because that's going to be your midpoint of your path. Okay, your y velocity at the peak, you're no longer traveling up or down, so your vertical velocity is 0. So going back to our velocity vector, we're going to set the y component equal to 0. We're going to solve this for t, and we're going to end up with u sine theta over g. Okay, that's the halfway point, which means that the final time, if we just multiply this by 2, because all parabolas are symmetric, So the final flight time is 2u sine theta over g. Okay, so now we're just going to try and show that the value of theta that we got from before gives us two t values that are less than this. So they're both occurring before we land. So they're actually in the flight time and they're actually real solutions. Okay, so let's go back to our equation from before for t. This was on the previous slide. We're now going to actually solve this using the quadratic formula, which is a bit of a mess, but it looks like this. So we've got negative b out the front, our discriminant from before, which we've already looked at, and on the bottom we've got 2 times a. Okay, so remember our goal is to try and show less than this eventually, but we'll circle back to that. Splitting this apart and doing a bit of simplifying, I'm going to pull the half out the front and split away my 2 terms with a g on the bottom, okay, because I'm trying to make it look kind of like this, which is the challenge for this question. So we've got 3u, we can cancel the g on the top here, and we can pull a g squared out of the square root, which is going to turn it into a g. Cancels one of the g's on the bottom, so this g squared turns into a g. Okay, I'm saying g a lot, but this one cancels, and there's a g in here that we can pull out that cancels as well. Okay, there's also a u squared inside that we can pull out of both factors, and then when we pull it out of the square root, it becomes a u. That's how I got that right there. And now we are just going to pull the g out the front, pull the u out the front because we've got a common factor, and now we're looking at this inside of, just imagine there's a bracket there because I'm not going to go back and fix that, but yeah, there is a bracket there. Okay, so now we're going to try and prove an argument to show that this can be shown to be less than this. The way we're going to do that is by looking at what's inside the square root. We're going to say that 9 sine squared minus 8 is less than 9 sine squared, which is true, okay, because this is going to be, because we're taking away 8 from it, we're going to be taking the square root of a smaller number, so this will be less than this, which is less than 3 sine theta. What this means is that we're doing 3 sine theta plus or minus something that is less than 3 sine theta. Okay, so that means that this is going to give us 2 positive values, because if we were doing 3 sine theta, take away something that's bigger than 3 sine theta, we would get a negative value, which doesn't work because we're trying to solve for t. T is time, time can't be negative, okay? So what's inside here is less than 3 sine theta, which means this thing here is giving us 2 positive values because we're not going below 0. That's what this argument here is trying to establish, okay? 2 positive values, both solutions for t are greater than 0. That's good. Now we know that they're both 0, we're just going to check that they are less than this, and then we're all good for our full 5 marks for this question. Okay, so going back to our values for t, which we solved just here, okay, this expression just here, here's where it gets a little bit dicey. We're going to write that our expression for t, which we've solved for, is less than the same thing, but we're changing this 8 to an 8 sine squared. The reason we can do that is because sine is a function that oscillates between -1 and 1, which means that the value of sine squared is always going to be between 0 and 1. Okay, so we're always multiplying 8 by something that's either making it the same size or it's making it smaller. Okay, for that reason, we can say, and of course theta is not equal to 0. For that reason, we can say that 8 is greater than, 8 is greater than 8 sine squared theta. So we're taking away a greater number. So this left-hand side is smaller than this right-hand side. Okay, that's the bit of a head scratcher for me, but once you stare at it for a bit, it starts to make a bit of sense. All right, that means we can write the right-hand side as 9 sine squared, take away 8 sine squared, which is equal to 1 sine squared. When you take the square root of it, it turns into sine. So now what's in here is 3 sine theta plus sine theta, or actually we're less than that, okay? That's good because 3 sine theta plus sine theta is equal to 4 sine theta, and then 4 over 2 is going to turn into 2. So this whole thing turns into 2u sine theta over g, which is what we were trying to prove, okay? So what we've proven is that there are 2 values for t. They are both positive, so they both occur within the flight time. And because the larger one can be shown to be less than 2u sine theta, the larger value for t is within the time of flight, so it's all working out. So for 5 marks, we have shown that there are 2 values of t for which theta gives us 2 vectors which are perpendicular, which is a lot to say out loud. And then we've shown, to get the final mark, that the larger value of t is less than the time of flight, so it actually occurs before the particle lands. And there is your 5 marks. Oh my god, that was hectic, but we got through it. All right, hopefully that gave you some better understanding of how to approach HSC level projectile motion questions. And if you want some more practice, I recommend either Howard Mathematics for exercise, or if you have an access to Smarter Maths, they have a good bank of projectile motion questions from past Extension 1 HSC exams, which are really good practice. Okay, cool. Thank you so much for watching. Hopefully catch you in the next mechanics video. Bye for now.